When we talk about electric vehicles, the first image that comes to mind for many people might be a futuristic, streamlined body, or that giant touchscreen on the center console, or perhaps the amazing autonomous driving and assist systems. But in reality, all these cooling technologies are just the surface of EVs. If you strip away the shell of an electric car, remove the fancy interior and software, you will find that the essence of an EV is actually just a giant chemical reactor mounted on 4 wheels. All the challenges currently faced by the EV industry, all the range anxiety, all the safety controversies, and even vehicle pricing strategies, ultimately pointing to the exact same core physical and chemical bottlenecks, which is the battery. Before we dive deeply into the differences between various batteries on the market, we must first understand the impossible triangle dilemma that automotive engineers face every day. The 3 vertices are energy density, safety, and cost. The laws of physics are very harsh. At the current stage of materials science development, you cannot perfectly satisfy all 3 conditions simultaneously. If you want the car to run very far, you must increase the energy density. This means you have to pack extremely active chemicals into a tiny space. But this inevitably increases the risk of fire significantly, which means sacrificing safety. If you put safety first, using extremely stable chemical materials, then the battery's energy density will decrease. You won't be able to store much power in the same volume. Not only will the car not run far, but adding more batteries to increase range will make the car body extremely heavy. When the car becomes heavier, the motor needs to consume more electricity to push the vehicle. This forms an unsolvable vicious cycle. And if we want to balance both decent range and extremely high safety, we would have to use very rare and expensive metal materials, or adopt extremely complex battery packaging and cooling technologies. This would cause manufacturing costs to skyrocket exponentially, leading to persistently high prices for electric vehicles, making them impossible to popularize in the mass market. So, automakers and battery manufacturers are actually trying to find a balancing point in this impossible triangle that best suits their product positioning. And the choice of this balance point is reflected in their choice of battery chemical materials. To understand this material war, we first need to understand the basic operating principles of a lithium-ion battery. You can imagine a lithium-ion battery as a valley with 2 peaks. The left peak is the anode, and the right peak is the cathode. In between is a valley filled with electrolytes. And in the middle of the valley, there is a filter that only allows specific personnel to pass through. We call this the separator. The key player here is the lithium ion. When the battery is discharging, which is when you step on the EV accelerator to drive the motor, lithium ions travel from the anode, swim through the electrolyte, pass through the separator, and finally reach the cathode. This movement process drives electrons to flow in the external circuit, generating the current that propels the vehicle. When you are charging, this process is reversed. The powerful voltage from the charging station forcibly pulls the lithium ions out of the cathode, making them swim back to the anode to be stored. Because lithium ions swim back and forth between the anode and cathode like this, scientists have also vividly dubbed this kind of battery the rocking chair battery. In this rocking chair mechanism, for the vast majority of EV batteries in the world today, their anode materials don't actually differ that much, which is the main component of our pencil leads. At most, a little silicon is doped into improved performance. The electrolyte and separator technologies are also relatively standardized. What truly makes a huge difference in EV batteries? Determining whether this battery provides phenomenal range or acts as a fortress of safety all comes down to the cathode material. The cathode material is like a parking lot for lithium ions. How many cars this parking lot can hold determines the battery's capacity. How sturdy the building structure of this parking lot is determines the battery's lifespan and safety. And what rare building materials are needed to construct this parking lot determines the cost of the battery. The cathode materials that currently dominate the EV market are mainly divided into two major camps. One is the ternary lithium battery, which pursues ultimate performance. The other is the lithium iron phosphate battery, which focuses on safety and affordability. Let's first talk about the ternary lithium batteries, most favored by high-end EVs on the market. The so-called ternary means its cathode material is composed of three transition metal elements. The most common combination is nickel cobalt manganese, abbreviated as NMC in English, or nickel cobalt aluminum, abbreviated as NCA. Tesla's early models, as well as many flagship EVs from traditional automakers that emphasize performance and long range, are all die-hard supporters of ternary lithium batteries. Why use these three metals? Because they each play an indispensable role. First is nickel. Nickel is the absolute main force for increasing energy density. You can imagine nickel as the contractor, responsible for expanding parking spaces in the parking lot. The higher the proportion of nickel in the cathode material, the more lithium ions it can accommodate. The battery capacity becomes larger, and the car naturally runs further. Therefore, the battery industry has always had a clear development trend called high nickelization. From the early days when the ratio of nickel, cobalt, and manganese was 1 to 1 to 1, it gradually developed to 5 to 2 to 3, and then to 8 to 1 to 1. This is the NCM 811 battery often mentioned in the industry, where the proportion of nickel is as high as 80%. This brought the energy density of batteries to unprecedented heights. But there is no free lunch. Although nickel can increase capacity, its own chemical properties are very active and extremely unstable. When the proportion of nickel is too high, the stability of the entire cathode structure drops significantly. It's like building a skyscraper with fragile bricks, with the danger of collapsing at any time. This is when the second element, cobalt, is needed to save the day. Cobalt plays the role of stabilizing the structure in a ternary lithium battery. It's like the steel skeleton of this skyscraper, responsible for firmly fixing the volatile nickel within the crystal structure, ensuring that as lithium ions frequently enter and exit the parking lot, the building will not easily collapse. Cobalt is crucial for maintaining the battery's cycle life and structural integrity. However, cobalt has two fatal flaws. First, it is very expensive and is known as the black gold of the battery world. Its price fluctuates wildly, directly choking the throat of battery costs. Second, a very high proportion of global cobalt mines are concentrated in the Democratic Republic of Congo. The mining process. It is often accompanied by harsh labor conditions and human rights controversies. This makes many automakers pursuing corporate social responsibility feel very troubled. This is also why major automakers use every possible means to develop cobalt-free or low-cobalt batteries, because once reliance on cobalt is shaken off, battery costs can drop significantly, and supply chain risks can also be reduced. As for the third element, manganese or aluminum, they play the roles of buffering and supporting. Manganese has very stable chemical properties. Adding manganese can effectively reduce thermal reactions inside the battery, improve overall safety, and simultaneously lower costs slightly. Aluminum has a similar effect, capable of strengthening the stability of the overall structure. Although ternary lithium batteries push energy density to the limit through the perfect ratio of these three metals, it also brings its biggest hidden danger, thermal runaway risk. The cathode material of ternary lithium batteries is very unstable at high temperatures. When the battery generates high heat due to a severe car crash, chassis punctures, overcharging, or internal short circuit, and the temperature reaches around 200 degrees Celsius. The crystal structure of the ternary material will begin to disintegrate violently. What's even more terrifying is that this disintegration not only releases a massive amount of heat, but also releases pure oxygen. Everyone knows that the three elements of combustion are combustibles, a heat source, and oxygen. In a sealed battery pack, the high-temperature liquid electrolyte is an excellent combustible. The short circuit provides the heat source, and the disintegrating cathode material unexpectedly acts as its own oxygen supply equipment. Once these three conditions are met, it will trigger a terrifying chain reaction. The internal temperature of the battery will surge within seconds to 600 degrees Celsius or even over 1,000 degrees, and then trigger a violent fire or even an explosion. This is why we occasionally see news of EV fires, and the fires are often very fierce, making it difficult even for fire departments to quickly extinguish using conventional methods. Because the battery is continuously self-supplying oxygen internally, it can continue to burn without needing air from the outside. To suppress this performance beast, automakers must invest massive R&D costs to design extremely complex and heavy liquid cooling and heat dissipation systems, fiery retardant layers, and sophisticated battery management systems to ensure that the temperature and voltage of every single one of the tens of thousands of cells are under the strictest monitoring. This also indirectly increases the overall weight and cost of the vehicle. Having talked about the high-risk, high-reward ternary lithium batteries, we turned our attention to the other camp, lithium iron phosphate batteries, also known in the industry as LFP. If ternary lithium is an F1 race car driver pursuing extreme speeds, then lithium iron phosphate is a steady and grounded heavy-duty semi-truck. As the name suggests, its cathode material is composed of phosphorus, iron, and lithium elements. It perfectly avoids expensive nickel, and there is no morally controversial cobalt. Its raw materials are very abundant on Earth and easy to obtain, and it's incredibly cheap. This directly solves the cost pain points faced by the automotive industry, making the large-scale popularization of affordable EVs possible. But the biggest selling point of lithium iron phosphate is actually its almost absurdly high safety. This is thanks to its unique microscopic crystal structure. Under a microscope, lithium iron phosphate exhibits what is known as an olivine structure. In this structure, between the phosphorus atoms and oxygen atoms, an extremely strong chemical bond is formed, called a covalent bond. How strong is the bonding force of this covalent bond? Even if you heat the battery to 500 or 600 degrees Celsius, or conduct an extreme nail penetration test, piercing directly through the battery to trigger a severe internal short circuit, the structure of lithium iron phosphate remains as steady as Mount Tai. It absolutely will not disintegrate and release oxygen like ternary materials do, without the assist of oxygen. Even if the internal temperature of the battery rises due to a short circuit, the internal electrolytes will at most boil and smoke. It's extremely difficult for intense burning to occur. This is exactly what family cars that treat safety as their supreme guiding principle, along with taxi fleets and large commercial vehicles, dreaming of in terms of chemical characteristics. Beyond ultimate safety, this sturdy olivine structure, it also brings another massive benefit: super long cycle life. Because the cathode structure, during frequent charging and discharge processes, is not prone to deformation or microscopic collapse. Lithium iron phosphate batteries can withstand over 3,000 or even 4,000 full charge-discharge cycles, and the battery capacity can still maintain a state of health above 80%. Let's do the math. This means if you charge your EV from 0 to full every single day, This battery can last for 10 or even 15 years. The lifespan of the battery is often longer than the lifespan of the vehicle's chassis and suspension system. This is also why many large, grid-scale energy storage stations today, as well as electric buses operating at high intensity in urban areas every day, have comprehensively switched to lithium iron phosphate batteries without hesitation. However, just as we mentioned at the beginning with the impossible triangle, physics will not let you have it all. Lithium iron phosphate has achieved absolute safety and super long lifespan, but the heavy price it pays is extremely low energy density because iron and phosphorus have relatively large molecular weights, coupled with the physical limitations of the crystal structure itself. The number of lithium ions that lithium iron phosphate can internally accommodate, it is far inferior to high-nickel ternary lithium materials. Under the same volume or weight, the electrical charge carried by a lithium iron phosphate battery is only about 60% to 70% of that of a ternary lithium battery. This means that if a car model using lithium iron phosphate wants to achieve the exact same long range as a ternary lithium model, it must pack in a battery pack with a much larger volume and an astonishingly heavier weight. This will not only severely squeeze interior seating and storage space, but the significantly increased vehicle weight will also make the car extremely sluggish. Acceleration performance worsens, and cornering handling deteriorates. At the same time, the heavier vehicle body will consume more electricity while driving, canceling out part of the hard-earned increase in battery capacity. In addition to this, lithium iron phosphate has another innate fatal weakness, which is extremely poor low-temperature performance. In extremely low-temperature environments, the liquid electrolyte inside the battery becomes very viscous. This causes the movement speed of lithium ions within the solid crystal structure of lithium iron phosphate to drop significantly. The entire chemical reaction becomes extremely sluggish, and internal resistance spikes. If you live in a high-latitude region that gets snow, in the dead of winter at -10 degrees, if you leave an EV equipped with a lithium iron phosphate battery parked outside overnight, you might wake up the next morning devastated to find that the range on your dashboard has been slashed right in half. Even the power for instant acceleration will be limited. This is also why, in cold regions like Canada in North America and Northern Europe, ternary lithium batteries still hold an irreplaceable market position. Having said this, we can deeply understand why major automakers have divergences and compromises when it comes to battery pathways. Building a car has never been as simple as taking all the parts with the best specs on the market and stuffing them entirely into a car shell. Instead, under various harsh physical limits, cost considerations, and market positioning, it is the ultimate engineering art of seeking the optimal solution. A few years ago, there was a mainstream voice in the market that believed ternary lithium was the future of EVs, and that lithium iron phosphate, because of its low energy density, it was a backward technology that would eventually be phased out by the market. But actual developments harshly slapped down this overly optimistic technological myths. In recent years, with breakthrough advancements in battery packaging technology, such as BYD's Blade Battery or CATL-CTP cell-to-pack mobile-less battery pack technology, engineers have demonstrated ultimate ingenuity. They boldly eliminated the complex module casings and structural support components inside traditional battery packs, saving all the space that was originally used to hold the metal framework, and densely packing in more lithium iron phosphate cells. Through optimization of the physical structure, this approach significantly improves space utilization, thereby compensating for the energy density flaws of the chemical materials. This has successfully increased the total power of the entire lithium iron phosphate battery pack. allowing EVs using the LFP system to comfortably achieve a range that solidly crosses the 500-kilometer threshold that general consumers can fully accept. This engineering breakthrough has completely changed the landscape of the global EV market. Automakers have found through data that, for the vast majority of consumers who only commute within the city and occasionally take intercity trips, a true range of 400 to 500 kilometers is entirely sufficient to cover 95% of usage scenarios. These mass-market consumers actually don't need to force themselves just for a long cross-country trip that might only happen once or twice a year to bear the exorbitant purchase cost of a ternary lithium battery, as well as the lingering safety anxiety regarding thermal runaways and fires in their minds. Therefore, we see the EV leader Tesla comprehensively switching its standard range Model 3 and Model Y to lithium iron phosphate batteries. Traditional giant Ford's Mustang Mach-E, and even the entry-level series of many traditional European luxury automakers have all embraced lithium iron phosphate. Automakers are calculating their commercial strategies very precisely. They use cheap materials, long-lasting, and absolutely safe LFP batteries to significantly lower the selling price, seizing market share in the massive mass-market entry segment, and then reserve the expensive, high-energy density ternary lithium batteries for those pursuing extreme acceleration of braking 100 kilometers per hour in 3 seconds, frequent long-distance driving, and high-end luxury performance models for buyers who completely disregard the high car prices. This is absolutely not a technological regression, but a display of the perfect combination of commercial logic and engineering physics. However, whether it's ternary lithium or lithium iron phosphate, current compromises are ultimately just transitional solutions in the industry's development process. Humanity's desire for longer ranges, faster charging speeds, and absolute safety is endless. Since we know that the flammable liquid electrolyte inside the battery is the chief culprit causing all thermal runaway risks, and since the physical limits of existing cathode materials are already difficult to break through and double again, what is the next move for top global scientists? The answer is very clear. Completely replace the liquid electrolyte. This is currently the ultimate holy grail that the entire battery industry is pouring hundreds of billions in funds into frantically researching the solid-state battery. The principle of a solid-state battery, frankly, is not complex. It simply takes the liquid electrolyte that originally flows like water inside the battery and replaces it with solid ceramic polymers or sulfide materials. This seemingly simple change in material state can bring an earth-shattering revolution to the entire industry. First, the solid-state electrolyte itself is non-flammable. This equates to directly removing the fuel for battery thermal runaway from a physical level. Without flammable liquids, the battery's safety performance reaches unprecedented heights. In the lab, you can cut open a solid-state battery, chop it up with scissors, or pierce it with iron nails, and it won't explode or catch fire. Secondly, because the solid electrolyte is extremely hard, it can act like a physical defensive wall, physically blocking the growth of lithium dendrites. What are lithium dendrites? In traditional liquid batteries, if you frequently use ultra-high-speed fast charging, lithium ions don't have time to safely return to the carbon structure of the anode and will pile up on the surface of the anode into destructive, tree-like metal crystals. Once these sharp metal crystals continuously grow and eventually pierce the thin separator, it leads to direct contact between the anode and cathode, causing a severe short circuit. This is also a major reason why many EVs suddenly caught fire at charging stations today. Solid-state electrolytes completely solve this fatal problem. This means that, in the future, We can even directly discard the heavy graphite anode and switch to pure metallic lithium for the anode. Once this is achieved, the battery's energy density will directly double. Future EVs will easily break through over 1,000 kilometers of true range and will be able to withstand extreme high currents, realizing an ultra-high-speed fast charging experience, where a 5-minute charge can run 500 kilometers.